Hi everyone, myself is Sahadeb Mahata. I got a PhD admission offer from NISER in experimental condensed matter physics, and I secured rank 82 in JEST 2022 and 920 rank in GATE 2022. So in NISER, they will first conduct a written exam, and after that they will call. If you selected in written exam, they will call for interview at the same day or the next day. And I was given interview on 4th June, and I was called for interview on 5th June. Okay, so in interview they asked me to introduce myself, and after that they asked me in which subject I am comfortable, as they will start with that subject. So I said that I am comfortable in quantum mechanics, statistical mechanics, and condensed matter physics. So the first question was in they asked me to solve the Schrodinger equation for a free particle in a circle, and what will be the energy and wave function for this case. So now for free particle in a circle, free particle in a circle, uh, free particle means the potential is zero, and then we can write the Hamiltonian is rotational kinetic energy plus potential energy, and as potential energy is zero, then Hamiltonian will be is equal to the rotational kinetic energy. Okay, now for two dimension case, Hamiltonian can be written as h squared square by 2m, where m is the mass of the particle, del 2 del x2 plus del 2 del y2. Okay, now what is del 2 del x2 plus del 2 del y2 in plane polar coordinate? It will be del 2 del r2 plus 1 by r del 2 del theta 2 plus del theta plus 1 by r square del 2 del phi 2. For a free particle rotating in a circle, here r and theta is constant. As r and theta is constant, then this term and this term is going to be 0. Okay, so there is only one term, there is only phi term. So the total Hamiltonian then can be written as del 2 h square by 2m r square del 2 del phi 2. This is the total Hamiltonian for a free particle in a circle. Now Schrodinger equation is h psi is equal to E psi minus h square by 2m r square del 2 del phi 2 is equal to E psi. Okay, we know the moment of inertia is equal to m r square. So we can put here minus h square by 2 I del 2 del phi 2 E psi, del 2 del phi 2 plus 2 I E by h square psi is equal to 0. We are assuming it as m. Okay, we are assuming it as m. So m is equal to 2 I E by h square under root m square it is. So solution of this equation, solution of this Schrodinger equation will be in this type, let's say a to the power I m phi in this type. Okay, now using the boundary condition, we know that for a particle in a ring, the wave function repeat itself after the period of 2 pi. So psi of phi is equal to will be phi plus 2 pi, and psi of phi is equal to I m phi plus equal to e to the power I m phi plus 2 pi. E to the power I m phi is equal to e to the power I m phi e to the power I m 2 pi. The left hand side and the right hand side will be equal if this term is equal to 1. Okay, so e to the power I m 2 I m pi is equal to 1. That means m can take value 0 plus minus 1 plus minus 2. Okay, so now what will be the expression of energy? In the previous slide we have written that m is equal to, we expressed it, m is equal to 2i by h cut square. So m is equal to under root 2i e divided by h cut square. So e is equal to m square h cut square by 2i. This is the expression of energy, and here for m is equal to 0, energy is 0. For a particle in a ring, ground state energy can be 0, and for m is equal to 1, energy is h cut square by 2i, and for m is equal to minus 1, energy remains same, 2i. So it is twofold degenerate, okay. So then they asked what will be the expression of wave function. The wave function will be psi of phi is equal to a to the power I m phi. So using the normalization condition we can find the value of a, and it will be 0 to 2 pi psi star of phi d phi is equal to 1. In the using this condition we can get the value of a. Okay, now then they asked the second question from quantum mechanics. They asked me to draw the potential barrier, and after that they asked me for case E greater than V and E less than V, what will be the nature of the wave function in each region. So I was asked to draw the potential barrier. So potential barrier, this is 0 to a, region 1, region 2, and this is region 3. Okay, this is V. Here V of x is equal to 0, G0 and 0, x less than 0, 0, x less than a, and x greater than a. This type of potential. Okay. They asked me what will be the nature of the wave function for the case E greater than V naught. If we take energy more than the potential, then what will be the nature of the wave function in edge region? So in this region, if we solve the Schrodinger equation, minus h cut square by 2m del 2 psi del h2, potential is 0, is equal to E psi. So we will get sinusoidal nature. Psi of x is equal to a e to the power I k x plus b e to the power minus I k x. This is the solution of these equations, and the first term represent the incident wave. This is incident wave, and the second term represent the reflected wave energy level. I assume the energy level is more. This is the energy level than potential. It is more than potential, and this is for first region. And for region 2, the wave function, the solution of the Schrodinger equation will be del 2 psi del x2 plus v of x psi of x is equal to e psi of x, and del 2 psi del x2 plus e minus v 2m divided by a square psi of x is equal to psi 2. So psi 2 will be a b c d c e to the power I k2 x plus d e to the power minus I k2 x, where k2 is 2m e minus v divided by h square. Okay, so in this region, the second region, the wave function is oscillatory, and the first region it is also oscillatory, and as potential is 0 here, so in the third region the wave function will be oscillatory. It will be in this type. But in the second region the amplitude will be larger, because in second region, let's draw it in the this is v0, this is v region 1 0 to x 0 to a, region 3 region 2, and sorry, k2 was 2m e minus v by h square. Okay, and we know the wavelength is equal to h by t. Okay, so okay, don't write it. Lambda k is equal to 2 pi by lambda. We know that k is equal to 2 pi by lambda. So lambda is equal to 2 pi by k, and k1 was 2m e divided by h squared. We can say that k2 is less than k1. K2 is less than k1. This is lambda 2. So lambda 1 is 2 pi by k1. So we can say that lambda 2 is greater than lambda 1. Wavelength in the second region will be larger. Wavelength in the second region will be larger than in the first region. This is, and in this region it will be like that. Then again it will be this. It will be larger. This is lambda 2, this is lambda 1. Okay, and then they asked, for the case E less than V naught, what will be the nature of the wave function in each region? For the case E less than V0, what will be the nature of the wave function in each region? This is the energy level and this is the potential. region 1, region 2 and region 3. Okay, so in first Schrodinger equation in for first region, del 2 psi del x2 plus 2m e, potential is 0 here, sorry, plus, not plus, good, e psi. So in first region it will be oscillatory in nature, a e to the power I kx plus b e to the power minus I kx. But for the second region, for region 2, Schrodinger equation 2m del x2 plus v of x psi equal to e psi del 2 del x2 minus 2m v minus e divided by e square psi of x is equal to 0. So del 2 del x2 plus k2 square psi of x is equal to 0. Here k2 square dash is equal to, it is negative sign, sorry, it is negative sign, k2 is equal to 2m v minus e divided by e square. And the solution for this wave equation, will be psi of x psi of x c e to the power I k2 dash x plus d e to the power minus I k2 x. From this we can see that it is a type of decaying function. Okay, this type of decaying function, and if we draw the wave function in this region, it will be decaying. Okay, and in the region 3, the potential is equal to 0, then it will be oscillatory in nature. So this will be the nature of the wave function for the case E less than V naught. So these were the questions from quantum mechanics. Then they asked me from solid state physics or condensed matter physics. They asked to draw the energy band of insulator and semiconductor and matter and metal. It will be metal. Okay, so this is the energy level. This is valence band and this is conduction band. And between valence band and conduction band there is a energy gap called forbidden gap, energy gap or forbidden gap. Okay, so it is about 6 electron volt it is about 6 electrovolt. This is for the case insulator. This is for the case insulator. Okay, and this is conduction band. It is about 1.2 electrovolt. Uh, this is for semiconductor. This is, and for metal, this is valence band, and this is conduction band. There is no forbidden gap between conduction band and valence band for metal. They overlap each other. These are the band diagram for insulator, semiconductor, and metal. Okay. After that, they asked me draw the EK diagram for electron and band theory of solid. So for free electron theory, we know that for free electron theory potential is 0. It is assumed constant or 0. Okay, and the energy is only kinetic energy. So the energy term is in terms of k square is h cut square k square by 2m. This is the energy in free electron theory. In free electron theory, so it is parabola. The relation is parabola. E is equal to h cut square k square by 2m, and for band theory of solid, we assumed that the potential actually not 0. Okay, the potential is not 0. It is periodic potential. The potential is of periodic type. So when we are introducing periodic potential, and after that, if when we are solving the Schrodinger equations using periodic potential, then we are not getting this type of dispersion relation. We are getting this type of EK diagram. Okay, at pi by 2, at minus pi by 2, this is the first Brillouin zone. This is the first Brillouin zone. This type of EK diagram we are getting, and here the energy is 0 at pi by a and minus pi by a because of Bragg reflection. In band theory of solid, it is 0 here because of Bragg reflection, and then at pi by 2, 2 pi by a and minus 2 pi by a, it is 0. So the energy level are discrete. Energy level are discrete. In this case, for free electron theory, we are getting that the energy level are continuous, but here energy level are discrete. This is the discrete amount of here is the energy gap. This is called the, and this is the allowed band, and this is the forbidden band, forbidden energy band, and this is due to the Bragg reflection. Actually, when we solve the Schrodinger equation using the periodic potential, we will get this type of relation. So now they asked me for PN junction, explain how current flow and how can you calculate the depletion region. So I said that if the PN junction is in forward bias, that is if it is the P region is connected to the positive terminal of the battery, and this is the junction. Sorry. This is N type. So if the positive terminal it is uh, connected, this is plus, this is minus voltage, this is N type. These are the holes and these are the free electrons. So if the for a PN junction, if the positive terminal is connected to the P type and the negative terminal of the battery is connected to the N type, then the majority carriers will push toward this junction. This is the depletion region. This is the depletion region. Majority carriers will push towards the depletion region, and in depletion region they will be recombined, and due to their recombination current will start to flow. Okay, so in this way, if it is in forward bias, then current will flow. For a PN junction, if it is in forward bias, then current will flow. And after that they asked me then how you can calculate this depletion region. I said them using this formula, 2 epsilon by q 1 by Na plus 1 by Nd. Na is the acceptor concentration and Nd is the donor concentration, into Vbi. Vbi is the built-in potential and V minus V is the applied voltage. Using this formula we can calculate the depletion region, depletion width. So these were the interview questions from NISER. Okay, and one more questions was there from quantum mechanics. In these questions they asked me, for the case E less than V naught, the potential barrier, this is 0 to A, this is V naught, the energy level is E. Okay, so we know that in the region, this is region 1, this is region 2, and this is region 3. In region 1 the wave function naturally is oscillatory, and in for energy less than V naught in region 2 wave function will be exponentially decaying. Sorry. And in region 3 it will be again oscillatory because there is no potential. Okay, now they asked me, if I changed or if I shift the origin, if I shift the origin here, this is the 0 point and this is the minus a by 2 and this is plus a by 2. Now potentially symmetric, v of x is minus of x is equal to v of x. The potential is symmetric, and we know that if potential is symmetric, then wave function should be symmetric. But for this case, as it is exponentially decaying, that means it is in the form of e to the power minus kx. So it is neither symmetric or neither antisymmetric. This wave function is neither symmetric or neither antisymmetric. So why it is not symmetric or not antisymmetric in this case? But potentially symmetric here, but wave function is not symmetric here. What is the reason for that? And at that time I was not able to explain these questions, and yet not I don't know what will be the answer of these questions. Okay, so this was the interview experience from NISER, and there is no questions. Okay, thank you.